So I actually only really have one story, and it's something that you might have noticed right at the start of the year. There was a big astronomy conference held in Hawaii. It was the 235th American Astronomical Society meeting, and there were a lot of results that came out of it. But then one of the stories that came out was the so-called Radcliffe wave, and hit the press, and so you could see it for. Showed up in BBC, CNN, lots of press, not only all around the country, but all around the world. And I thought I would talk about this just because it is kind of a weird little topic that people who are not in this particular field might not know about or might not understand the significance of. So even though there were a lot of interesting stories coming out of the conference, I'm just going to focus on this tonight. And so basically, before we can talk about what the Radcliffe wave is, let's talk about how stars form and what galaxies are like. So this is another galaxy. This is not our galaxy, but this is a face-on galaxy, and it gives you a good picture of what our galaxy might look like if we were able to be outside of it and look back and take a picture. So obviously this is not something that we can do with our galaxy. Our space probes have barely left the solar system. This is a spiral galaxy just like our own galaxy with a hint of a bar. I think our bar at the center is more distinctive than this. And in spiral galaxies, what you really notice are the spiral arms, that pinwheel-like shape that's defined by these dark dust lanes. So notice in addition to the stars, there are these brownish patchy regions that outline the spiral arms. And then what you also notice are these red kind of bubbles, these blisters that dot the spiral arms. And those are locations where stars have formed. So those dark regions, those dark lanes, are places where there's lots of molecular gas, cold clouds of gas that can collapse gravitationally and form stars. And what we found in the universe, and this is true not only in our galaxy, but in other galaxies that we've observed, is that stars tend to form in lots and lots of them all at once. So these clusters here probably contain many tens of thousands of stars. And the reason why they're glowing red in this picture is that out of those tens of thousands, you might have a handful or a couple dozen of really massive stars that put out huge amounts of ultraviolet radiation, and they have very powerful winds, and the radiation and the winds basically carve out this giant bubble of hot gas in the molecular cloud that they're born from. And so what you're seeing is this excavation going on, and that red glow is from the ionization of hydrogen gas. And so when we look at spiral galaxies, and even when we look at our own, we see hints of not only all of this, but star formation taking place. And of course, our view from planet Earth is something like this. So this is a panoramic image. You're not just seeing just a portion of the sky. You're seeing quite a bit of the sky that's flattened, and you're seeing the Milky Way, which is this band of light that crosses the sky. And the reason why we see the Milky Way is because we live inside the disk of our Milky Way galaxy. And in a really long exposure photograph like this, you can also make out the dark gas lanes that exist in our galaxy, just as you see the dark clouds that exist in other galaxies. And then even here, you can see little hints of red that tell you places where there are young stars forming, and those the massive young stars are ionizing the gas. We also talked briefly about, let's take a closer look at what one of these gas clouds look like. So this is an isolated cloud called Barnard 68, and there are no stars forming inside of it, but unlike other clouds, this isn't surrounded by lots of other cloud-like features. It's sort of hanging out by itself in interstellar space. And all around it, you see background stars. So we're basically looking in a direction where there might be a few foreground stars, like here and here, but for the most part, everything is off in the distance behind the cloud. And then what I should point out is look at the edges of the cloud, and you'll see that the cloud is a little bit transparent right at the very edge. And what happens is that as you move from off cloud onto the cloud as you're observing, the stars start to disappear, but notice that the stars get redder. So what's happening is that the gas and the dust in the cloud is basically subtracting out the blue light from the stars. So as you go deeper and deeper into cloud, you have the reddest stars over here, and then finally the stars completely disappear in this image. And this is taken in optical wavelengths, so this is the same sort of light that our eyes are sensitive to. Now if you switch to the infrared, what you'll find is the cloud becomes almost transparent. And so there isn't enough gas and dust to completely block all of the infrared light, and so you can see through the cloud. But if this cloud was a lot thicker or a lot more opaque, it would block these particular wavelengths of infrared light. But in this case, there is still starlight getting through. All right, so we've introduced the idea of molecular clouds, and I just want to give you a brief primer on how star formation works. So as I said, molecular clouds are the sources of young stars, of new stars. And what can happen is that, again, portions of the cloud can collapse, and you can have a cluster of stars that are inside or embedded inside the cloud, so they're hidden away. But then over time, if you have some massive stars forming, those stars with their radiation and the winds can blow out the cloud, and the radiation can ionize a big bubble of hot gas. And then there are other winds and outflows from even the lower mass stars as well. But over time, the cloud is broken up by all this activity generated by the young stars. And then one final thing that can happen is that the most massive stars at least 8 times the mass of our sun, can go supernova. And that can also not only completely disrupt the cloud, but there's some evidence to suggest that the shock waves from the supernova can cause clouds further away to collapse and induce further star formation. So there is some evidence that star formation is self-limiting in the sense that it can destroy the original cloud that your stars are coming from, but it's also propagating in the sense that it can continue new star formation further away in more distant clouds. All right, so with that sort of star formation introduction, I want to now go back 150 years and talk about Benjamin Gould, who was an American astronomer, and he was actually the first American to get a what we think of as a PhD or a doctorate in astronomy. He went to Germany and studied mathematics and astronomy under Carl Friedrich Gauss, who was a very famous mathematician and physicist. And he came back to the US. He started the Astronomical Journal. He started observatories. But one of the things that he noticed was that if you went out into the nighttime sky, you could actually trace a line connecting a bunch of bright stars. And this is a modern map that someone has traced out. So in the background, in this kind of dark purple, is the Milky Way. And in the yellow, or the kind of the gold orange, is the band that we now call Gould's Belt, or the Gould Belt. And so this basically, this band outlines a number of bright stars and a number of constellations that include Orion and Perseus and Taurus. These are locations where people have seen lots of star formation activity, but it's really curious that all these different star forming regions would lay on a circle surrounding us. And it doesn't even exactly align with the galactic plane, the plane of the galaxy. It's actually tilted by about 20 degrees. And so here is another view of it. We're taking the galactic plane and flattening it out. And you can see that red band shows the location of Gould's Belt. Gould's belt happens to have perked the interest of a lot of astronomers. So someone has counted that there have been over 2,200 scientific papers that have been written about it over the last 100 years. And the consensus is that if you look at the young stars that were formed and the young clusters that were formed, the initial beginnings of the belt probably started about 30 to 60 million years ago with the first wave of star formation. And right now it has a diameter of about 3,000 light years. So it's a pretty giant object in our Milky Way. As I said, it's tilted compared to the galactic plane. And there's been a lot of speculation as to what could have caused Gould's belt. Why are all these young star clusters lined up in this belt-like shape? And people have offered ideas such as what if they're expanding waves of star formation? So the idea that supernova or stellar winds propagate star formation to other clouds. And so Gould's belt is basically these multiple waves of star forming that have propagated outwards. People have also some early ideas suggest it could have been just a young star cluster with lots of young hot stars that have expanded out in a ring. Maybe it's just a rotating disk of clouds, and so because it's rotating, that gives you the initial shape, and all these clouds are forming stars, and that gives you the Gould belt. Another idea is perhaps there's another cloud that's coming from out of our galaxy, and it's slammed into the disk of our Milky Way, and that has led to this ring of star formation in that ring. And then finally, as different ideas become popular in astronomy, you also get more speculative ideas like instead of just a high velocity cloud, what if it's a dark matter cloud that's impacting? So there have been a lot of ideas, and people have done a lot of work. So this is a paper from 1992 showing, so the Gould belt is actually this ellipse here that's in dash marks, and they're pointing out the locations of young star clusters and clouds. Here's a more recent paper from 2003 where we're looking down onto the plane of the galaxy, and again remarking on the belt. And then from that same paper, they're showing that view in 3D where all these little spheres are locations of young star clusters. And these units are in order, or in parsecs, and so a parsec is about 3¼ light years. So again, we're talking about something that's pretty significant in size. And then here's a paper from a couple years after that, where the authors actually went out and found measurements for the distances to various stars that they could associate with the Gould belt. And so here, this top figure is where they're looking at down again on the belt, and you can vaguely see a hint of an ellipse, although it's you have to kind of defocus your eyes to really see it. But here we're looking at a side view, and that tilt is a little bit more evident. And then this bottom plot is another side view. Here's a paper just from a couple years ago where they're using Gaia data, and I'll talk about the Gaia satellite in just a minute, where again, these points represent clusters of stars, and they think they have a pretty good idea of how the stars are moving, and so they're fitting this ellipsoid, this flattened sphere, onto it to show how all these stars and clusters of stars could be associated with this Gould belt. All right, so that brings us to the press release which came out earlier this month, and they have a paper coming out in the journal Nature. It's actually not quite out yet, so I had to dig around to try and find as much information as I could. But the team is led by Joao Alves, who's at the University of Vienna, but he's been working at the Radcliffe Institute for Advanced Studies at Harvard University. And the team there is led by Alyssa Goodman, who is a professor at Harvard. And the third person in the picture is Catherine Zucker, who's actually a graduate student of Alyssa's. And so in a number of papers written over the last year plus, and then culminating in this, they've been kind of leading up to this Radcliffe wave result. And then obviously the Radcliffe wave is named after the Radcliffe Institute for Advanced Studies, but I'll talk a little bit about why they named it that too at the end. But what they did was to use data from the Gaia satellite, and the Gaia satellite is a satellite put up by the European Space Agency. And the idea behind this is to really accurately map the locations, the three-dimensional locations of over 1 billion stars in our Milky Way galaxy. And so this is a map of our Milky Way generated by the stars that were detected by Gaia. So you can see that they really did cover much of our, all of our nighttime sky, and these places where you think you're seeing dark clouds, those are actually regions where the starlight is being blocked by the dust and gas. And then you're also seeing the large and small Magellanic Clouds. So they really did an excellent coverage. And in order to get a three-dimensional position of stars, what the satellite does is use a technique called parallax. And this is something very simple, or at least simple to think about. And this is a simple activity that everyone who's ever taken an astronomy course has done. But what I want you to do is to hold up one thumb about, let's say, 6 inches from your nose. And if you can close one eye and then the other, you'll notice your thumb will flip or move relative to the background. Now, what happens if you move your thumb to arm's length instead of only 6 inches away? What happens? Yeah, it shifts by a smaller distance, and that's just because your thumb is further away, and so it has less, or it appears to move less. And astronomers have been using this technique for many decades, first from ground-based telescopes, and now with space-based observatories to basically measure that type of shift. But to use that, what you do is you measure it. Gaia is in orbit close to the Earth, and so as the Earth orbits the Sun, you have this very long baseline from one end of the solar system to the other. And so if you're observing a foreground star, you'll be able to see hopefully see a significant shift of that foreground star against the background stars. And so here is an animation showing how this would actually work. And so what we're seeing is what Gaia would see as the satellite is orbiting, is around the Earth, but it's orbiting the Sun. And so you'll see stars do this circle motion over the course of a year. And depending on how far that star is, the further away the star, the smaller the circle. And so basically by making really accurate measurements of the positions of stars on the sky, you can get an idea of how far they are based on how big of a circle or ellipse they track in the sky. Now it's a little bit more complicated than that because stars are not stationary. All stars in our galaxy, including our sun, our nearest star, are in orbit around the center of their galaxy. So even though they're all roughly orbiting in the plane in the same direction, there's enough different relative motions between one star versus another that this simple animation doesn't quite work. And so what you have instead is something like this, where the stars don't end up with closed tracks. Instead, they have these loop-de-loops, and then depending on, so that star on the right is moving really fast because it has what we call fast space motion, and so you hardly see that circular motion. And so, and you can imagine this is really complicated once you start tracking over 1 billion stars. Okay, and then what the Gaia team has done is they've done an animation showing what this might look like for all the stars in one direction in the galaxy, And here they've exaggerated the parallax motion, that circular motion, by a factor of 100,000. So normally, these are really small motions that you wouldn't be able to see with your eye, but here, because of that exaggeration, you can see how the closest stars, again, have the biggest circles, and then the further stars have little tiny circles, and then the further stars still, you can hardly see move. And then we're going to turn on actual what astronomers call proper motion, meaning now we see how the stars move. And in this case, the motions, they're side-to-side motions, are exaggerated by a factor of 1 trillion. So it's basically by doing these sort of observations that you can build a three-dimensional picture of stars in our galaxy. And even with that, Gaia has observed just under 2 billion stars total, but that's still a tiny fraction of the estimated couple hundred billion stars in our galaxy. So even with this, we know we're not sampling all the stars in our galaxy. All right, so what Joao Alves and his team did was they used Gaia data for specific lines of sight that were towards regions where there was known star formation. So this is a molecular cloud map of the galaxy. That's what all these dark regions are. And you can see that all these blue circles represent locations where they've looked. And the way that they determine the distances to these clouds, I mean, you can get distances to the stars, but you need to be able to figure out where the star forming regions are. And so you have to find the distances to the clouds that host the stars. And so we go back to this picture where, again, remember that if you have stars that are just behind the cloud, they start getting reddened before they disappear. And so they use this fact that starlight can be reddened by molecular gas to basically start plotting stars in a particular direction. So here we're looking towards Orion, and they're finding lots of stars that don't have any reddening at all. And then here are all the stars that are reddened, and these numbers up on the side show you the amount of reddening or the amount of light that's been absorbed by the cloud. And so you see that there's this kind of almost like a hard edge where suddenly the stars more distant than that edge are reddened. And so that tells you that the molecular cloud must start right about here, and that all the stars that are forming stars as part of that molecular cloud must lay further than the edge of that right there. And so basically by using this technique and on all those lines of sight, this is the result that they get. And so our sun is located here with the circle and the dot in the middle. And all the red dots are star-forming regions and their associated molecular clouds. And then there are also a bunch of other star-forming regions. But what is really curious now is that instead of getting a belt-like feature or an ellipse, everything is in a line, which was unexpected, to say the least, because for over 100 years, people have been talking about the Gould belt, and here, with really accurate measurements, they're seeing a line of star-forming regions instead of ones sort of in a circle. And then here's that circle of Gould's belt. So there are still some regions that are part of that ellipse that makes up the Gould belt, but a lot of other star-forming regions that were thought might have been closer are now clearly not part of that ellipse. And oops. You go back, and here I actually have a three-dimensional interactive. Okay, so here is that line of star-forming regions again, where we're looking down onto the plane of the galaxy. And then if we take a side view, what you see is that line is actually not completely flat. It's actually a wave, which is hence why it's called the Radcliffe wave. And then the other really interesting thing is that if you look at it on n from the other direction, it's also extremely narrow. So it's almost like a ribbon that's undulating through the plane of the galaxy. And so, this top-down view might not have been completely unexpected, although it was unexpected, but we do see, this sort of lines up with where you might think a molecular or a spiral arm of the galaxy would be. And then we can also turn on, but the fact that that sideways view gives you this wave, that was definitely unexpected. And then we can also turn on the Gould belt schematic. And then we can see that, from the top, it looks like things do line up. But if you start tilting off to the side, you can get one or two groups of star-forming regions to line up, but it's difficult to get all of them to really line up. So it seems like Gould's belt is kind of a fiction that astronomers didn't realize was not real for about 100 years. And we've had our paradigm kind of overturned by this. All right, so the question is, why were astronomers so wrong about this? And basically, the reason is that measuring distances is really difficult in astronomy. You can measure the location of something on the sky really accurately, but trying to figure out whether it's far away or close by is more difficult. And so it turns out that with Gaia and with this new dust mapping technique, we're using the reddening of stars to really determine the distances to clouds. That's changed the uncertainties from about 30%, which is what they were before, to about 5% now. So basically, whereas before, you didn't really have a hint of this wave-like nature with much lower uncertainties and much better distances, these features just pop out. And this is a cartoon, so it's not exactly what's going on, but it gives you roughly the idea. And so basically, we've gone in 150 years from this view of what we think it was the Gould belt to this, where you clearly have something in line that you can imagine being part of a spiral arm, although it's also super straight, but it's about 9,000 light years long and about 400 light years across. And its estimated mass is on the order of about 3 million solar masses worth of gas and dust and stars. So it's, in the press, they were calling it the largest gaseous feature in the galaxy that's been discovered. And right now, the big question is, what caused the wave? And so instead of the question of what caused this ring, now the question is turned to what caused the wave. And this is something for the theorists and other observers to start thinking about. So perhaps a collision with a molecular cloud or high velocity cloud from interstellar space, intergalactic space, that could be an idea. Or there could be other things that could perturb those, the gas into that spiral pattern. Now, I want to go back to why they named it the Radcliffe wave. And one reason, obviously, is it's named for the institute where much of this research took place. Radcliffe College was a women's school that was associated with Harvard University. So 100 years ago, women and men went to separate colleges, and so the men went to Harvard and the women went to Radcliffe. And since then, the schools have combined, so there isn't any gender segregation anymore. But it turns out that João Alves named the wave after Radcliffe because of some of this history. And specifically, for Henrietta Leavitt, who graduated from Radcliffe College. And she is very famous, not during her time, but later as being a female astronomer, which were extremely rare back then when she was working, and for making some extremely pioneering discoveries. And so what she was working on was measuring the light from stars that we call Cepheid variables. And these are stars that actually vary in their brightness. And this is a plot from a paper by Hubble. But basically what we're seeing is the number of days along the bottom. And this is magnitudes, which is an astronomer's way of measuring the brightnesses of stars. And what you find is that it starts out dim, but over a course of several weeks, it brightens, and then it decays, and then it brightens, and it decays. And depending on the star, you have different brightnesses, and they decay and brighten over different periods of time. And they also have different patterns by which that decay happens. And Henrietta Leavitt was part of a team of roughly about 80 women who worked at Harvard Observatory. And they were called computers because one of the jobs of computers was to do actual calculations, but in this case they went and made measurements of photographic plates. So back then they took photographic plates of the sky, and people were really interested in variable stars since nobody understood why they were variable. And so they carefully recorded the brightnesses of stars. I mean, here is a plate from the Small Magellanic Cloud, so you can imagine how many stars there are in this plate, and then trying to record all the stars that you could measure, and then do it over time to find the ones that are variable. So this is an excruciatingly tedious type of task, but women at the time were paid up to about, I think, $10 a week to do something like this. But instead of just doing work like this, she actually went and figured out what was happening with these Cepheid variable stars. So this is a very important paper from 1912 that appeared in the Harvard College Observatory Circular. And if you look at the bottom, you can see that the paper is written by Edward C. Pickering, who was the astronomer who was in charge of that program of observers. But if you look at that first line, that sentence, it says, the following statement regarding the periods of 25 variable stars in the Small Magellanic Cloud has been prepared by Miss Leavitt. So what that means is that she actually wrote this whole thing, and the guy just attached his name to it. And that's because at the time, again, because of sexism and the perceived role of women in society, women were not allowed to author scientific papers. They had to do it under a man's name. And sometimes if their husband was also an astronomer, they could author a paper under his name, but it was rare for a woman to be able to put her name on this. Now here is the really important plot in the paper, and what Henrietta Leavitt did was she plotted the period, meaning how long it took for these variable stars to vary in their brightness, and then along the y-axis, the vertical axis, she plotted how bright the intrinsic brightness of these stars were. And so she basically found that there is a relationship between how fast these stars varied versus how bright they were. So the brighter the star, the longer it took for it to vary. So this is in days. And this is a log-log plot where she took logarithms and showed that you could have a very simple relationship between the period and the luminosity. And this is extremely important because it basically gave you a way to measure distances in space. Because if you knew how quickly something varied, then you knew what its intrinsic brightness was. And that told you how far away it was. And at the time, she was measuring these in the Small Magellanic Cloud, and nobody knew what the distance to the Magellanic Clouds were. But within a year of this paper, another astronomer, Hertzsprung, had come up with measurements of Cepheid variables much closer, and which he was actually able to measure the distances of. So with this plot, astronomers were now able to measure distances to distant galaxies. And so in the 1920s, Edwin Hubble discovered Cepheid variables in the Andromeda galaxy, which is we know now to be over 2 million light years away. And basically, using her work he and other astronomers, and of course, there was still a lot of work that they had to do, but this was the beginning of our understanding of how big the universe is and our realization that the universe is expanding. So I think it's really appropriate that the Radcliffe wave was named in part because of the inspiration of Henrietta Leavitt's work, because she did pioneering work on distances to other stars, and the Gaia satellite helped us establish distances to distant stars to help us upend our ideas of what is in our nearby galaxy. All right, I've run for way too long, so thanks, and I'm going to turn it over to Steve.